My presentation today will be about what we refer to as the continuum limit of a closed-permeate system. And mostly, I guess most of you are interested in the interacting case. So how do we get from this abstract setup we have in mind, or we want presented today, to the equation of motions from the standard model. And this is like mostly referring to the blue book, which is also titled the continuum limit of closed-permeate system, and also some of my recent work together with Felix. And the main goal is we start with Minkowski space time as a non-interacting system as a critical point of the causal action, and then we look for perturbations around this critical point. And from that, we use the causal action, which we also know already, to derive dynamical equations for these perturbations. And then, as it turned out, these dynamical equations have a variational form, so we can write down an effective Lagrangian for that. And this Lagrangian corresponds to the Lagrangian of the standard model. And whenever I refer to the standard model, I will not talk about any second quantization on that. Everything will be first quantized compatible if you want. And then if you have the effective Lagrangian, you basically can do second quantization as you used to from your QFT vectors. Okay, so let me just quickly recap the objects we had so far. So we have these local correlation operators, which I denote by x, and think of them really as points in Minkowski space time. Also, as it was shown before, we have this identification between points in R4 to these operators by identifying the spin inner product with the Hilbert space inner product. So we have these operators S. And then we also have the physical wave function, which is just a projection onto the image of such an operator. And these define then in the smooth setting sections over M in the spin bundle. And then also we have seen so far the evaluation operator and the kernel fermionic projector. And just recently we got introduced this closed chain where we just multiply K of xy with adjoint with respect to spin inner products. And then what was also shown by Sebastian that AXY has the same non-vanishing eigenvalues as the operator product XY. So basically what that gives us is that we can purely formulate the causal X or the causal Lagrangian in terms of the closed chain, or be more precise in terms of this kernel of the fermionic projector. So let me just write it down on the blackboard maybe to what I have in mind there. So instead of considering the points xy, I will now consider the Lagrangian of this closed chain, and here is the same as what Felix introduced this morning. We have the sum over the eigenvalues, 1 to n, and then we take the difference of two eigenvalues of it and then square it, which gives us the causal Lagrangian, and then the actual principle is still the same. But just to keep in mind that it's sufficient to know the eigenvalues of x and y to fully evaluate it. Because all other eigenvalues of the operator product x and y are 0, so they don't contribute here. Okay, and then as a next step, I want to introduce you the restricted Euler-Lagrange equation, which you can derive from the Euler-Lagrange equation, which Felix presented also this morning. So let me start with the Euler-Lagrange equation. We have this function L of x, and in contrast to what Felix showed, I also introduced this parameter r, this math fraction parameter r in front of the trace, which accounts for the trace constraint, so also as a Lagrange multiplier. And then the restricted Euler-Lagrange equation we know Felix told us that L of x is minimal on space-time, and one condition to get out of it is that the first derivative on m is 0 there. Okay, so how do we make this equation more precise, or how can we reformulate it? And for that, I will look at the perturbation of these local correlation operators x, which, as you know, corresponds to the, or also corresponds to the weight evaluation operator, because the adjoint of the weight evaluation operator is just x restricted onto the spin space, so we can also treat it as a variation of that. And then, since I only vary one point, namely x, not the y where I integrate over, I get that the variation of pxy is given as a graph, and then if you have the adjoint, you vary, of course, only the other one, and then you can write down the variation of the closed chain just by applying the product rule. Okay, then we continue and plug that into the Lagrangian, and there we just, as I wrote down here, I just treat it as a function of axy. Since axy is a matrix value, I have to take the trace here when I want to express the derivative, and I can rewrite it as 2 times the real part of the trace, where I only have the variation of pyx, not xy anymore. And the qxy is what I get out of taking the derivative of this Lagrangian. And similarly, I have to apply this variation for the trace, because I want to only consider variations with which are allowed under the trace constraint. And then what I get is, when I have this L of x and have the first variation vanishes, I got that 2 times the real trace of the old expression has to vanish for all the variations delta psi, which corresponds then to this equation here. And this is what we refer to the restricted Euler-Lagrange equation. Okay, so this will be a very helpful equation in the following, so just try to remember it, and mostly we will focus on this q in this expression, which I didn't write down explicitly, but you just get it by taking the derivative of the Lagrangian with respect to axy. Okay. Any questions so far?
So you are restricting the trace to be 0, or it should be a constraint to be a constant, no?
Yeah, and then since okay, I restrict it to be it has to be a constant, and then I can implement this constraint by this Lagrange multiplier.
Yeah, but then it should be in parentheses tau, parentheses, and then the s inside the parentheses, right?
But the s is from the volume constraint. But you get also, like,
but if you vary relative to tau, you say that you get that the trace is 0, not a constant. Okay, 0 is a constant. But
no, well, let me just, because this is just a little L, you have to impose it at the level of the action. So what you refer to this term here, where you have this trace of x minus this constant.
Yeah, that's what the Felix wrote.
And then, you apply this at the level of the Lagrangian, not at the level of the Euler-Lagrange equation. And then, basically, you have to derive the Euler-Lagrange equation, and then you get this term.
That's the integrated Lagrange.
Also, for the s, you would have the similar expression there. You would also have that s times d rho of x minus the other constant from the volume constraint. And you don't see that in this equation.
Okay.
Any other questions? Okay. Then let me just also recalculate quickly what the choose a representation of our Hilbert space H as the negative energy solutions of the Dirac equation. Then we choose as the spin inner product, the usual Dirac inner product with gamma 0 in there. And as I mentioned before, we have this identification between R4 and curly F. So we know how to map points in our space-time to operators in this curly F. And then we also have the measure, which is just a push forward of the back measure on R4. And then you also see that if you have this construction of your measure, then the support of your rho is just the image of R4, so it's isomorphic for R4. And the physical wave functions are just evaluating the solution of the Dirac equation at a point x. Exactly. And then, of course, what I used here for writing down this equality, I used the identification of the spin in spin space, which is just isomorphic to C4. So you really see this here. And I will also use this identification through my whole presentation. And then, if you use that, you can write down the kernel of the Fermi-Magnetics projector explicitly, which has this form. So you first of all has this k slash plus m term of gamma mu, k mu plus m mu. Then you have this delta squared minus m squared term, which also comes from the Dirac equation. And then we have projection onto the negative energies, and then also the Fourier transform. And importantly, we can write it as this derivative of this solution of the Klein-Walton equation. And for those who might be a bit familiar with quantum field theory in curved state spacetimes, this pxy is nothing else than the negative frequency by solution, Weigand function, for the Dirac equation. Or the t is the negative frequency Weigand function of the Klein-Walton equation, and then taking the derivative gives you the fermionic version of it. Okay. So are these clear so far? Because this is basically the starting point of people analysis. So first of all, I want to talk a bit about the singular structure of this pxy. So again, might be more familiar to you to express it in a common notion, which is the Hadamard expansion of it. So first of all, we have this txy, which is the solution of the Klein-Walton equation, which has the leading singularity of 1 over xi squared, with xi squared equals y minus x. And then for this pxy, we just get one more derivative out of it as the leading singularities. And in another way to think about it is this, what I wrote down on the right-hand side, is t0 term and the derivative with respect to the mass parameter of this t, which is known as the Schwinger-Dirichlet expansion. So you can think of txy as just one term of this Schwinger-Dirichlet expansion, and then similar writing down this pxy, we get two terms, and if you want to look at more complex systems, not Minkowski vacuum, you get a whole series expansion there, and we will get to that.
So what was the definition of the XY? The definition
Of the txy, just
this was the definition.
yeah, you think of it. So this is just the definition here. If you pull out this k slash plus m term in front, which gives you the derivative plus the m, then the remaining integral is just this txy. And this is the Weigand phi solution of the Klein-Walton equation. Okay, and extend t to t minus I epsilon, and this corresponds then to a regularization. Yeah?
So you have just t minus 1 in the bracket.
Yeah.
-1.
You mean, yeah, you can, so if you look at t's like above, as they are defined, then you see that when you take the derivative of that, you get psi slash over 2 in front and reduce the exponent by 1, and you can take that as a definition of that. So it's basically, so you can also introduce this in the other way around. And then,
So derivative.
yeah, so the t's have a very, like, from a technical point of view, you can take the derivative of Tn, or think of it Tn plus 1, and we have n greater than 0, so we can use the definition above to, and then you see that they satisfy this property. And then you define t minus 1 just by extending this. So you take the derivative of this t0 term, which you know, and you see that this has the form psi slash over 2, and then you get something else here, and this is the t minus 1. So you use basically this as the defining equation for that.
So this derivative with respect to n square, when I write t as this integral, they get me down some exponent, and to the minus 1 is just, I take the exponent 1.
Yeah, exactly. And this also works in globally hyperbolic space-time if you don't have like well-defined Fourier integrals. Okay, and if you do that, so we have this pxy explicitly, we introduce this regularization, and we can compute axy, and we compute the eigenvalues, and then we find that in the limit of epsilon to 0, we get that this q, what I showed you before, this derivative is 0. So if we choose this Lagrange multiplier r to be 0, we see that the Minkowski spaceline is indeed a critical point of the coordination system. Okay, so next I want to, as I introduced before, we want to look at perturbation about this, around this critical point. And how can we do that? One approach to do that is to just perturb the Dirac equation underlying it. So we just insert some perturbation E, which at this point just has to be a linear symmetric operator acting on only the x arc of this pxy. For example, we can think of a differential operator, we can think of an integral operator, and then also we can think of like local vector or vector potentials or just multiplication operators from a mathematical point of view. So I will now talk about differential operators. Integral operators will be also discussed when we go to the color theory or to the quantum field theory limit. But for now, I will only consider plain multiplication operators, and I start with what you will think of as a maximum potential there. So I want to consider the following Dirac equation, just inserting an arbitrary vector potential there. And then, of course, I need to find the pxy again. And I do that iteratively, so I start with P0 as the vacuum space-time, and then I get the ends in nth order in A by solving the second line here. Okay, and then what do we get? We're at first order in A, so we have this pxy, and you do like apply Green's methods to solve it, you will find that px tilde looks something like that. And now I want to go through the terms, term by term. So first of all, the first line is just a vacuum up to higher order terms. Then the second line is a phase factor, which you pick up by this A, which when you consider it in the Lagrangian drops out because of the absolute value of the eigenvalues. And then the third line is the one of interest, which gives us the equation of motions for this vector potential. And then I can also comment like the third line vanishes, the fourth line gives also some further constraints or conditions on the current, and then everything else is higher order corrections in there. When you take the limit epsilon to 0, of course. And then you do the whole procedure again, so you compute AXY, then you compute the eigenvalues again, and then you get QXY out of it, and then up to now I haven't imposed any conditions so far on this AXY. It's an arbitrary vector potential, but now I have the restriction that my QXY has still to be 0 in order to satisfy the Euler-Lagrange equations. And this is exactly the case when psi mu times the current, the Maxwell current vanishes, where psi is a like-like vector. And since this has to hold for all psi, of course, the current itself has to vanish. So I got the homogeneous Maxwell equations for the vector potential out of the cross section. And then, as I commented before, of course, you all recognize this equation, and this is a variational form, so we can write down an effective Lagrangian, which is just the usual Maxwell Lagrangian. Okay, now what to do next? And also think of other variations. For example, we can add a positive energy solution to the pxy. And then we do the same procedure again, and we get that in addition to the Maxwell current, we get this V bar gamma mu, V bar as V term. Again, only evaluated when contracting with a like-like vector because of the singularities. This is the only term we get out of interest in the limit epsilon to 0. And yeah, this corresponds then to the inhomogeneous Maxwell equation, or the theorem Maxwell equation.
So in the discussions for this were related from 0 to A evaluated in design, which means you're evaluating the A and complex argument. Is that something to worry about?
Not necessarily, because you always have, you can always extend it holomorphic around the real. Because you only have a small imaginary part, and then if you take the limit epsilon to 0, you're just in a very small neighborhood around the real line in your argument.
But A is not at all characterized, it's very generic A at the moment.
Yeah, exactly. And then basically by default action, we get the restriction that it has to, that the current has to vanish.
It's
The
generic.
integration makes sense.
Sorry?
It's generic or extendable complex argument.
Like, I think we already discussed about it. Like, you cannot just extend it any as far as you want, but for a very small epsilon, it's always possible to do that holomorphically.
So what do you want to extend the potential to the complex plane?
Yeah, because I have this I epsilon regularization.
It's because of T plus I epsilon. Where the strategy is where we can holomorphically extend it a bit too much, and you can just take like a Taylor expansion epsilon, which is then defined order by order, and the higher order than epsilon you can formulate anyhow because epsilon gets this.
Anyway, you only look at the limit epsilon to Okay, so we know so far how to do with one. So we have done a vector potential, and let's think about like the SU2 sector of the standard model or the strong interaction. So for that we need more fermionic sectors in our theory. So we don't consider n equals 2, so the spin dimension n equals 2, but rather we go for n equals 16. So, so we consider 8 fermionic sectors, which is in general by the causal action. If you want to think about it, you have this pxy, and it will be clear why I consider 8 fermions, which might not be a priori clear from the standard model. So in the vacuum, I have this, for each fermion, I have a p, as the one I showed you before, which has this form. And then what you have to introduce by hand is you have to somehow break the left-right symmetry of your theory. And what this does, when you plug it back into the causal action, we say that the 8th sector, I call it the neutrino, is only left-handed there. Then I get that this will couple to any other of the fermions. Let's call this one the electron. And what we get is that perturbations are allowed to interchange in this block. And also all the others, so I have P2 here, form blocks. So there we have an SU2 interaction. And then what remains to show, or what you can also do is then you can, with those 3 remaining blocks, you can also have another SU3 interaction here, which then gives you the strong interaction. And then the procedure is pretty much the same. You now, instead of just considering one pxy, you consider the direct sum of 2, and then you allow for perturbations which interchange between 2 of them. And then another perturbation you can think about is to consider linearized gravity, for example, with Minkowski and to have around that. Then basically what you get is that, again, on the line cone, you get this R mu minus T mu term in the equation for this Q tilde. And the interesting part is that here the regularization length appears as a prefactor of the curvature term. Again, only linearized around Minkowski. And since this is only valid on the light cone, of course, I have to somehow make, so the T mu is divergent free, so I need to somehow extend